This video is part of a course on food physics, of which this is the theory section. So this section has to do with single phase fluid flow, and other related videos are on heat transfer, mass transfer, and continuity, and so on. While the equations here are complete, this is by no means a replacement for a course on fluid mechanics, or it's not supposed to cover all of the details of what is normally done in a fluid mechanics class. It is done at the undergraduate engineering level. Again, this would be a quick derivation of the fluid equations at the undergraduate first course level, or even less than that, even faster than that. If you are looking for finer details that would be missing, the subject of fluid mechanics is one of the most well developed in engineering, and probably 100 textbooks exist on that. So you are kindly referred to those for details. So here we have a fluid element that's a control volume and with the size del x, del y, del z. So the volume, the mass of that element is delta x, delta y, delta z times the density rho. On this mass, I'm going to apply Newton's laws of motion. That is the basis of this derivation. It's momentum conservation and applying Newton's law. Okay, so I write force on that element is equal to mass times acceleration. So let me say a little bit about this capital D. So it's not, for now, the capital D just includes both kinds of acceleration. It's due to time, as velocity changes with time, but as the fluid moves into a region of higher velocity, it also gets accelerated. So both of these are included, and it's also known as substantial or total derivative. Okay, so and v is the velocity vector. So now I want to do these forces as per unit volume basis. So if I divide throughout both sides by volume, so my volume is this delta x, delta y, delta z. So if I divide by volume, then here also by volume, then I can write the force per unit volume. So this is force per unit volume is equal to density times the derivative of the velocity. Okay, so now this force that this element feels, we separate that into two parts. One is what it feels at the surface. So Fs is the surface forces, and then the other part, it is what it feels throughout the body. So this is a body force. So that's has nothing to do with the surface part, but it's what is felt throughout the volume. Okay, so now these are still vectors. So Now I want to write this equation only in the x direction, so only the x component. So I write Fs plus Fp is equal to rho times du over dt, where u is the velocity in the x direction. Now I'm going to write these forces in terms of the various components. Okay, so I define this quantity as Tij is the surface stress that is felt, where I stands for the normal to the surface, normal to the surface. So it's the direction of the surface, and J is the direction of the stress. So then if this is a surface here, this surface, the normal to it is in the x direction. So this particular stress is going to be Txx, meaning I is x. So I is x means it's normal to the x surface, and J is the direction of the stress, and we are interested excuse me, in the x direction only. But this is a finite volume, so the center of it is where it's Txx. So little bit far from the center at this surface, and the entire dimension being delta x, then at the surface it's going to be whatever is the value at the center plus the rate at which it changes with x, so del Txx del x, so rate at which it changes in this direction times the distance. So while Txx is at the center of the cube, on this surface here, it's Txx plus this quantity. And the same way it is on the other side, except that you're going backward, so it's going to be Txx minus del Txx del x times del x over 2. So with this definition, I'm going to write up all the components, all of the surface forces on the 6 faces that are occurring right now. I rewrite the equation from the previous slide, Fs plus Fb equal to rho d u dt, and now we're going to write all the x components of Fs. So let's start from this surface, the surface in the x direction. So the net force in the x direction is Txx plus del Txx del x times del x over 2. This is the surface stress, so this has to be multiplied by the area delta y delta z, which is the area of this face. So this is what's acting here, this guy, but there's also the one on the other face that we have to subtract. So minus Txx minus del Txx del x times del x over 2 times delta y delta z. So this is the net force that's in the x direction, net surface force. Likewise, we write y and z direction. So let's write the y now. So the y would be in a very similar way. It's this part. Tyx is the value at the center. So at the surface, this surface, it's Tyx plus del Tyx del y times del y over 2 times the area of this surface, which is delta x delta z. Likewise, on this face, Tyx minus del Tyx del y times delta y over 2 times the area, the surface area. This one is delta x delta z. Okay, and likewise, finally, we do for the surfaces in the z direction. Surfaces in the z direction, but forces in the x direction. So it's going to be Tzx here. This guy, Tzx plus del Tzx del z times del z over 2 times this area. This area is delta x times delta y. Delta x times delta y. Minus Tzx minus del Tzx del z times delta z over 2 times delta x delta y. So these are all my surface forces. So this is all, this is equal to my surface force, but my surface force is defined as, this one is defined as surface force per unit volume. So I have to multiply by the volume so that it's equal to the surface force, which is on the right hand side. Now we simplify. So you notice that this guy, for example, this one and this one is going to cancel. So we cancel those, and I also divide by this quantity on both sides. So I divide by that that quantity on both sides. So I write Fs is equal to del T del x, del Txx, I mean, del x plus del T Yx del y plus del T Zx over del z. So I have written the surface force in terms of the surface stresses Txx, Tyx, and Tzx. Now let's write the body force. So body force per unit volume. So body force times volume is equal to, what is the body force? So it will be, let's say, gravity. Gravity in the x direction. So this would be delta m mass times gravity in the x direction. So I would write Fb is equal to delta m over delta v times gx, which is equal to rho times gx. So what we have now is an expression for surface force and body force we're going to plug that into this equation and expand this term to get the final form of the equation. The equation then again, rho du dt is equal to Fs, the surface forces, which is del Txx del x plus del Tyx del y plus del Tzx del z plus body force, which is rho times gx. Now, at this point, we really skip a very significant step, and it's also a very involved one that we normally always skip in an undergraduate context, and certainly we will skip that here. And that is, how do I relate these surface forces to what we normally talk about in terms of shear force and normal forces and pressure? This relationship, like it's shown here, Txx is tau xx, which is the normal stress, and then P is the pressure. And likewise, the other values of T, we're going to change them to shear stresses, but it uses a whole set of relationships that come in more involved consideration of how the fluid is deforming. So from there, we can write, after doing that, we can expand this one, rho times del u del t plus u del u del x plus v del u del y plus w del u del z, where v is the velocity in the y direction and w is the velocity in the z direction. So this is equal to all of these other quantities like del Txx, del x plus del Tyx, del y plus del Tzx, del z plus rho gx. Now we substitute for these t's the relationships like this one. So when I do that, that's when I bring in shear stress and pressure. So once I do that, and that's unfortunately I have to skip all those both the detailed derivation of how we get these relations, but also just the plugging in part to finally get this. So you notice this guy is the same here, and the rho gx is still here. The rest of it is now changed from the surface stress to shear stress, and then we also have brought in pressure. So we are almost done deriving the equations. Now I will just rewrite the equation from the previous slide just to make it convenient. So we have all the same terms here. Now notice that so far everything we did has nothing to do with the type of fluid. It's just a force balance. It's just a statement of momentum conservation or applying Newton's laws. So now we have to bring in the fluid part. What type of a fluid it is, what type of a material is it? So those we bring in by having relations that relate the shear stress to properties of the material, which is viscosity. When the relations are like this, the way you are seeing here, then those belong to a class of fluid, the most common class of fluid as Newtonian fluid. So now we're bringing in Newtonian fluid, and these relations, so whether it's tau xx or tau yy, these relations for Newtonian fluid, we can plug these in here, right? We can plug in for tau xx and tau yy and tau zx. If we do, then we'll get equations that will have only velocities in there and this viscosity, of course. And if we do that, that's when we get this equation that you may have seen some versions of it. And so again, you notice some very important ones, several. One is, what is this equation? This equation is simply Newton's law, and it also, so if it is Newton's law, then it's going to be always valid. This is nothing special. This is going to be always valid. But this particular form here also uses these relations, which are for one type of fluid. So it's Newtonian fluid. So then these are for Newtonian fluid. So we have to remember that. And this is one component. This is only for U. We'll see in a second for the other component. But this, with the other components, would be what's known as Navier-Stokes equation. So then the Navier-Stokes equations is simply Newton's law applied to fluid, but of a Newtonian type of fluid. So here we have written the equation for all three components: velocity in the x direction, velocity in the y direction, velocity in the z direction. So far we had only derived this one, but a similar force balance can be done in y direction to get this one, and in z direction to get this one. So these are again the equations in Cartesian coordinate, and they are the Navier-Stokes equations because we already enforced the Newtonian fluid, and that's where this viscosity is coming from. Now, if you would like to see how these equations look in other coordinate systems, there are lots and lots of references that you can look up. Now, in vector notation, this equation would be written like this. So then this is the time derivative of velocity, and this is the spatial component. This is pressure, the viscous component, and the body forces. So in a software, in a commercial software that solves it, they will have the equation written in this format. But you want to see how each component came from simply doing force balance and a little bit of information about the fluid type. So these are very general. So the equation with all these different terms, so here I've only written it for the x direction. The equation with all these terms can be nerve-wracking trying to use them. So I would like to think of these as like the Swiss Army knife, that even though we have many different tools as part of it, we don't need all of the tools all of the time. So likewise, we don't need all of these terms all of the time. And so which ones do I need? It is much easier to actually deal with this equation, simplify, if we always relate the terms to their physical meanings. So for example, the first term here is due to time-dependent acceleration. So if the fluid flow is not changing with time, we do not need that term. The second one is due to acceleration with respect to space. And then third one has to do with pressures. And then the fourth one has to do with viscous forces. And finally, the fifth one is the body force. So again, another example, if the flow is horizontal, let's say, and gravity is not important, there's no other body force, then we don't need this term. So we don't need all the term all the time, but we should always, when we look at the equation, we should know where they came from. So this is again simply these are the forces, and force equal to mass times acceleration. So it's really a statement of the Newton's law of motion. Because it's very general, the equation is valid for any fluid as long as it's Newtonian. So it wasn't derived for any one type of food or something. Now, when the fluid is not Newtonian, then of course we need to make changes. That's discussed in the next slide. Now, we also did not derive this for any particular geometry. So it's valid for any size or shape, whether it's flow in a pipe, continuous flow in a pipe, or fluid flow in a container. It's valid all the time. And then the other part is that by having this general equation, by starting from it, it is always safer, because if we drop a term for good reasons, then we know exactly what physics we are ignoring. So it is always advisable to start from these general equations instead of starting from some ad hoc equations for one scenario. Of course, there are limitations of these equations. And to get around the limitations, we don't just throw these equations and get something else. We modify these equations. We use them correctly. We combine them. We generalize them. And here are the three examples I want to share. For example, if the fluid is non-Newtonian, like in this case, for a thick soup, we may need to consider a more general version of the equations, which means the force balance that we did is still fine, but instead of the Newtonian fluid, we'll use the descriptions of a more generalized fluid. However, even for a non-Newtonian fluid, if for example, the heating of a can, when it's not, the flows are not too rapid, then the Newtonian assumption would still be valid. So again, there are situations where we need to change, but lots of situations can be handled with what we just did. We can get away just assuming Newtonian. Now, another example is when multiple fluid phases are present. Then we have to develop more complex equations for multi-phase flow, but starting from the single phase equations that we developed. So the single phase equations that we developed, you can think of them as building blocks for the more complex situation. And perhaps the most important limitations of this equation for food is when we try to apply these to a solid or fluid flow inside a solid, we would have trouble, because if you look at this bread, for example, it has such complex pores and paths, while the equations that we derived are absolutely valid in those paths, but it's nearly impossible to handle that way. So when we treat food as a porous medium and we have transport of fluid, flow of fluid through the porous medium, then these equations would have severe limitations, and then we do have an alternate formulation, which is a formulation using a flow through porous medium, and some of you may know Darcy's law, and so we have a very different description of the fluid transport. This transport or the flow description of fluid through a porous media is discussed at length in a different module in this video series, or as part of this food physics course. So it's a separate module that you can look at for flow through porous medium.